We've already done a section similar to 11.7 when we're looking at similar figures in a previous chapter. In 11.7 we are looking at areas and volumes of similar solids. So kind of when we have similar in two dimensions, we're using a similar idea for the area, but we're also adding volume onto that. So similar solids, first of all, have the same shape, and all of their corresponding dimensions are proportional. So again, same shape, but not necessarily the same size. The ratio of corresponding linear dimensions of two similar solids is the scale factor. So that'd just be measuring like one side of a figure and comparing it to a similar side in another figure. Any two cubes are similar, as are any two spheres, because there's only one shape that we can have for that cube or for that sphere. So to practice and check if these two figures are similar in each question, we should be able to tell and also give the scale factor of the first to the second figure. So in our first example, it looks like we have not quite cubes because those lengths aren't the same all the way around, but those would be rectangular prisms. If I want to compare the scale factors, I can compare a side to a corresponding side in the other figure. So for example, it looks like the vertical segments are a 3 and a 6. Going across the front, we have a 3 and a 6 again, and we have the sides that are also matching 2 and 4. If we take those ratios and reduce all of those ratios, we get a scale factor of 1 to 2. So since we're using the same scale factor throughout the entire figure, that would make the two figures similar. So first of all, yes, they're similar. And also, since they used all the same scale factor, we can use that scale factor of 1 to 2. We see in part B, 2 to 3 would be the scale factor if I use the vertical component. If I measured the front, that would be 3 to 6. And we also have a 2 to 3 measurement for those matching right-hand sides. And it looks like two of them use the same scale factor, but across the front, if I use a scale factor of 3 to 6, that would reduce to 1 to 2. So since that scale factor is not consistent throughout the entire figure, those figures would not be similar. Last question, trying this with a cylinder. Looks like I can use the radii, would have a scale factor of 6 to 5. And since the heights are also in that ratio, if I took 12 to 10 and reduced it, I would also get 6 to 5. We could say that yes, they're similar because they use the same scale factor. That would be 6 to 5. You always want to make sure you use your reduced ratios as your scale factor. So instead of 12 to 10, we would list that scale factor as 6 to 5, which is reduced. So this is a little bit of a experiment sort of to figure out where we're getting our ratios from. Given the two similar figures, we want to find the following. Ratio of their side lengths would just be measuring again any linear measurement that corresponds. So 10. 2 meters to 4 meters, that would be a ratio of 1 to 2. If we wanted to measure the surface areas, we're just given the surface area measurements, although we could probably find those ourselves. If I use 22 to 88, that would reduce to 1 to 4 as a ratio. If I was trying to find the volumes, again, we should be able to find the volumes ourselves, but if we're given a 6 and a 48, if I get that ratio of 6 to 48, I should also be able to reduce that. That would make 1 to 8. So we should also notice a pattern happening between those three ratios, and this is where our rule comes from. If I already have a scale factor given of two similar figures, so again, if they're similar, they should have a scale factor in common. If the scale factor is a to b, then what we've seen before with areas is that area ratio is going to be a squared to b squared. Since we're adding volumes onto that, the only difference with volumes is that instead of that ratio being squared, it's going to be cubed. So the ratio of two similar solids is going to be a cubed to b cubed if we're finding their volumes. So putting that into practice, we could see questions like our first part of problem 2. If I start with square prisms, and a square prism would just be a cube, if they're similar, because all cubes are similar, we want to find the scale factor of the smaller prism to the larger prism. Although we're not given any linear measurements, instead we're just given a volume for the first figure and a volume for the second figure. So the first thing we want to do is to set up our proportion, and instead of saying a to b, that ratio is not 729 to 1331. If we're given the volumes, that would be a cubed to b cubed. Again, that's going back to the fact that the volume ratio is always going to be cubed. So if I set that up, a cubed to b cubed equals our first volume to our second volume. All I have to do for that to find a scale factor, the opposite of cubing something is taking a cube root. So if I take a cube root of my scale factor, or sorry, not my scale factor, my volume ratio, I just end up with my scale factor, so that would be a to b. If I take a cube root of that ratio we just had on the right-hand side, cube root of 729 would be 9. Cube root of 1331 should just be 11. So if I've taken the cube root of that original ratio, I get my scale factor, which is just 9 to 11. We can leave that as an answer for my scale factor because that's in simplest form. So trying that again, this time we're given surface areas, and that would be 144 square meters and 324 square meters. We still want to set up a proportion, but this time, since it's not a volume, I want to make sure that ratio is squared instead of cubed. So we know a squared to b squared would be equal to 144 to 324. And now if I want to get my scale factor, again, to get rid of a square, I just got to take the opposite of that, which is a square root. So square root at the top, square root at the bottom. I end up with my scale factor, a to b. If I do the same thing to the right-hand side, square root of 144 is 12. Square root of 324 is 18. I just want to take one more step to make sure I reduce that scale factor. So if I simplify that ratio, I can factor out a 6 from both of those, and I just get 2 to 3 as a scale factor instead. So always make sure we're answering in simplest form for our scale factors. So a couple other ways we could use that scale factor. We could be given lateral areas of two similar paint cans, and that would be 1019 and 425 for square centimeters. We also are told the volume of one can, and we should be able to use our ratios to find the volume of the larger can. So the first thing that we want to set up is we want to use the original measurements they were giving us. If they told us our lateral areas first, that should be able to get a area ratio from that. So if I put my two measurements as a ratio, 1019 to 425, again, since that's an area ratio, that should be the squared version of our scale factor. So that would be a squared to b squared. So what you want to do first is to find that scale factor. If I just take a square root of both parts of that ratio, square root of 1019, square root of 425, that would be our scale factor. We don't even really have to solve those as decimals just yet. We can leave those as square roots because that would be your scale factor. If we want to find the volumes, however, if we are given the volume of the smaller one and trying to use that to find the larger, we're going to set up another proportion, but this time instead of using that scale factor, again, since it's a volume ratio, that should be the cubed version of that scale factor. So we're going to take a to b, but cube both parts to have a cubed to b cubed. For the other side of that proportion, we want to make sure we put that new measurement for that volume, 1157. That should go on the bottom of that ratio because our smaller can went on the bottom of that previous ratio. So we want to keep that consistent. If I went larger to smaller first, I want to keep that as larger volume to smaller volume. And from there, all I've got to do is solve for that new volume. That capital V is what we don't know and what we're trying to find, that volume of the larger can. In order to do that, I can multiply both sides by 1157. And if I want to take the cubed scale factor, we knew the scale factor earlier was that square root 1029 over square root 425. I can plug that just right in, and the only thing I'm going to have to do is take that value and cube it, because we're looking at volumes this time. So if I take that scale factor and cube it, also multiply times the denominator of that right-hand side, that should all come out to 4,295 cubic centimeters. And again, a lot of that's just going to be done from the calculator. So trying that again, this time we start with volumes, and we want to use that to find an area, so kind of backwards from what we had before. We still want to set up our proportion to begin with, so if I start with two volumes, 128 and 250, I want to set that up as a cubed to b cubed is 128 to 250. Again, we're using cubed because that should be a volume ratio. Volume ratio is always cubed, not squared. First thing you can do on that is you could simplify your ratio. 128 and 250 are both even, so if I simplify, I get 64 to 125. And that way it's a little bit easier to see that when I take a cube root of the top and cube root of the bottom, cube root of 64 would just be 4, cube root of 125 is just going to be 5. So that finds our original scale factor. Since I started out with the cubed version for volume, if I take a cube root of both parts, I get my scale factor a to b, which is just going to be 4 to 5. And again, we're going to use that to find our new surface area. So using our next proportion, since it's area, that's got to be a squared to b squared, so areas are always squared. And just like that last question, if we were given the smaller surface area, or sorry, I guess this time it's the larger surface area, is 250 square meters. In our previous ratio, the larger measurement was on the bottom. So we want to match that in our new proportion. Whatever is larger is going to be on the bottom. So our new area that we're trying to find, that should be the numerator of that that right-hand side of that proportion. So just like before, if I know my scale factor, we did the work to find the scale factor was 4 to 5. Since I'm just looking for areas, I just got to take that scale factor and square it. And also, if I want to solve for that new area, I'd also have to multiply both sides by 250. So again, taking that scale factor, squaring it, and multiplying it times the denominator of that right-hand side, that should all give us 160 square meters for an area. So we can also do similar things with this. We can compare capacities and weights of similar objects. The capacity of an object is the amount of fluid the object can hold. So the capacities and weights of similar objects made of the same material are proportional to their volume. So this is just kind of a fancy way of writing some volume questions. So a bottle, for example, that is 10 inches high holds 34 ounces of milk. So this would just be like a milk bottle you drink out of. The sandwich shop shown below is shaped like a milk bottle, similar to that milk bottle that we described that was 10 inches tall. So to the nearest thousandth ounce, how many milk could the building hold? And we're going to find that by using, again, their original scale factor. If I know a linear measurement as 10 inches and it looks like we're given 480 inches for a measurement of that bigger milk bottle, that original scale factor would just be 10 to 480, or I could simplify that as 1 to 48. But again, if we're looking for capacity, I have to think about that in terms of the volume. So if I take that original scale factor and cube both parts, that should be equal to my volume. And again, if the smaller one holds 34 ounces, that's what we're treating as the smaller volume. We want to use that to find our bigger volume. So that's going to be our proportion. And all I have to do is substitute in my scale factor that we found from before, 1 to 48, just making sure we're cubing both parts since it is a volume ratio. And from there, if I want to solve for my new volume, all I got to do is cross multiply. So 1 to the third power is just 1, so I'm just left with v on one side of my equation. And if I do 34 times 48 to the third power, that should come out to this total of over 3 million ounces. And it says to round that to the nearest thousandth, although that should probably be 1,000 ounces. We can just leave our exact answer from what we found from before. So make sure you get some practice with this, answer the questions that follow, and we'll see how we do on this in class.